I did mention that I wasn't really sure whether I'd finish my slides in time, and I thought, well, I could always pretend I was Sriram and then just facilitate a discussion for half an hour. And given that Jeremy managed to basically fill this room with people for a discussion of languages like white space and brain fuck and the Shakespeare thing and intercal, and I think that probably would have been a better choice. But anyway, these pictures were generated by ChatGPT. The actual pictures of actually us are here. And anyway, I'm sort of going to be talking about exploring design space for runtime enforcement of dynamic capabilities, which is work being done by the big guy here, Andrew Fawcet, who, for family reasons, couldn't be here. And this is very much his work, and I thought this would have been an excellent topic for him to present as, the sort of first debutante coming out presentation as a PhD student, but he couldn't be here, which means I've got the luxury of a half-hour slot to fill, perhaps with not much content. Anyway, we shall see. You know who this is? For those of a certain age, Yosser Hughes. Yosser Hughes was a famous character from Boys from the Black Stuff, a 1980s British TV show, who was going around saying, "Giz a job," and that's there because I'm saying "giz a job" because I have been working as an independent researcher, but either I need another research contract or, a job. Anyway, and I said, should I put the "giz a job" in there? And Tobias says, of course you should. So anyway, there's nobody here from Jane Street in the room, so I'm probably screwed. Right. Other things happened in 1981 other than Yosser Hughes saying "giz a job." There was the ZX81, which actually was the first computer that I owned, which I was able to pay for from my... It's going to be relevant. What kind of? Relevant. It's at least as relevant as the joke I made about Lolland's language at the start of Jeremy's talk. The ZX81, I was able to afford that with a paper round, and it came with a number of interesting features. Well, really only three. A wobbly RAM pack that fell off, a really dodgy link to a television, and a cassette interface. 1981, okay? And I used that. Actually, I did get slightly better versions of the ZX81, but when I got to university in the mid-80s, we actually had, well, in fact, we had knockoff cheap versions of these VT52 visual terminals, okay? And then the other thing, of course, that happened in 1981 was IBM, produced this, the first IBM PC with a whole 256 kilobytes, or maybe it was only 128 kilobytes of interface, and you can see it's got a printer and it's got space for floppy disks and a cassette interface. Not many people know that. The first PC had a cassette interface. And by the second sort of generation things, they stopped pulling the cassette plugs out to the back of the case, but circuitry was still there on the circuit boards. Anyway, maybe this will be relevant. We'll see. Also in 1980, and it's like in another effing world, this was going on, right? Byte issue of Smalltalk, that's Smalltalk 1980, programs writing like this, and you couldn't... There's a different talk when I argue that the ZX81 is perhaps closer to Smalltalk than you might think, and certainly closer to Smalltalk than the IBM, at least the IBM PC running the standard operating system, although PCs were shipped with, was it 3 or 4 operating systems? One of which, USCD Pascal, was actually a hell of a lot closer to Smalltalk than you might let on, or Scheme. Anyway, that was Smalltalk, but at the same time, if you had a lot of money, you could have that, if anybody knows what that is. It is a standard screen grab from the Xerox Star. The Xerox Star, which was the first effectively commercially available thing with a graphical user interface. You're wondering what that's got to do with concurrency? We'll get there. That apparently cost $75,000 US and was hulking great. As somebody said, it was something the size of a fridge. It ran on a bit slice processor, which, strange as it may think, basically it meant, I think it was 16-bit machine, so it had effectively 16 1-bit processors that all worked in parallel, and each processor... Anyway, never mind. It's ridiculously cool stuff. And there we go, and that was 75,000 US. They figure, in inflation in Singapore or New Zealand dollars, that's about $500,000 just for one of those to get it. Believe it or not, at the same time, of course, Apple was producing that, if you know what that is, and I've decided that is actually a trick question. It wasn't supposed to be a trick question, but it is. Anyone? It's a Lisa. Well, that's right. It looks like a Lisa, the Apple Lisa. There were two. Apple really only made 4 computers. The Apple II, there was an Apple I, we don't mention that. It was the Apple II and a whole range of those things. The Apple III, which I had the misfortune of having to use, which also came out about 1981, and was their thing that they were kind of finding the IBM PC on the cheap. The Lisa, and then of course the Macintosh, which is we still have today, kind of. But that is a Lisa. Well, it's not actually a Lisa. It's a Mac XL. Because when in 1984 the Mac came along, it basically blew the Lisa out of the water. It was cheaper, it was more portable, and so what they actually did is, you can see this has got the 3.5-inch disk drive. The original Lisas had 5.25-inch disk drives that didn't really work, but you can actually see that's running macOS, or a hack version of macOS. If you've ever used it, it's horrible, because one of the big things about macOS was the pixels were square, but here the pixels aren't square. They were vertical rectangles, because that was how the Lisa worked, because they thought that's what you needed for getting high resolution for document production. This thing was, I think, something like 10,000 American, 60,000, so 10 times less the price of the Lisa, of the Xerox Star. And then the Mac came along, and here's what we start getting to the point of the talk, or I've wasted the first 10 minutes. That was my plan. Advertised as the computer for the rest of us. The computer for the rest of us. Because, you know, that thing cost $1,000 US, maybe $2,000 New Zealand dollars, maybe a bit more when it first came out. Sure, it was only 128K, and sure, it had some of the most sophisticated machine code ever written. In fact, it probably did have the most sophisticated machine code ever written for multiplexing floppy drives. Because it really needed 2 floppy drives, one for the system and one for the application data, or possibly the application program. And it had a memory manager built in that effectively gave you virtual memory on a 68,000 backed by floppy drives for your source code. But it could also actually store out RAM and back again. And, you know, you would call load a segment to load in a chunk of your program, and then it would go and find the floppy drive. And if, because you bought the cheap one with only one drive, the right floppy wasn't in the disk, it would sit there and say, would you please insert this other disk? And you then insert the other disk, and you waited while it crunched. What's this got to do with concurrency? Oh, we're getting there. If you look on the jargon file, if you look up for the rest of us on the for the rest of us on the jargon file, it says it's basically, you could think back to what Jeremy was talking about again. It's basically there's this entry here for the rest of us. And hackers have this piss take on that phrase for the rest of them. So whereas we can, you know, get in with soldering irons or COBOL or Intercal or machine code or higher order type theory or le roc, the programming language française, perhaps, the Prologue or Elgol or Eiffel or something, whatever these strange. Are there German programs? I don't want to think about that. There aren't any German programming languages. Plan calcul, yeah. I should say jawohl at that point, shouldn't I? Well, anyway, that remind me not to apply for a job remind me not to give this talk and make those jokes if I apply for a job in Munich. Anyway, look, they've got a much more sensible attitude than people losing control of their right arm while addressing a major political rally, I think, in Munich today than they do in freedom's land and bravery's home. Right, for the rest of them. And here, you know, sorry, I carry on, used in reference to software or anything which doesn't provide obvious capabilities because it's thought the poor losers might not be able to handle them. The rest of them, yeah, it's an attractive design to the rest of them, you know, they're stupid, blah, blah, blah. There's an awful lot of contempt because, you know, really, you should be a real bloke. You know, Paul Hexeth's kind of programmer without a beard. Programmers can't have beards, and they've got to wear proper shoes, and they've got to stand up straight, and got to be able to do the hard things. Yeah, right, fly the drones. You have to be very physically fit to fly drones. Not many people know that, you know. Sorry, you can't fly drones if you're a woman or a non-Christian. Quite how that works, I'm not quite sure, really, but anyway. So, I've been told I should tell people and try and get at least one big point across in the talk when I give talks, because then I talk to people a few months afterwards and they tell me what they think I told them, and it was nothing at all to do with what I wanted to get across. So, and anyway, Sophia's had to sit through many of my talks. She regularly experiences this. So, why I don't think this has been a terrible waste of time, and if you take one thing away from this talk, this is what I want you to take away. And in some ways I'm being really mean to many of the people in the room by putting this up. What's concurrency for the rest of them? Okay, what is concurrency for the rest of them? Because that is the underlying motivation for this project. And in a world in which JavaScript is apparently quite seriously planning to adopt all the ideas that were the best in when? About 1990, when we had them in Modular 3, and that were then copied and put in a language called Oak that was renamed Java. In terms of concurrency, and 25 years later, we're now thinking of putting those things into JavaScript, and when apparently, according to BS, I've mentioned that, apparently Python thinks that would be a good idea too. May Milano, who isn't here, has got really interesting stories. At least the Swifties, in some ways, are pushing back on some of the weirder stuff we would like to do. So. That's the idea around which this particular stream of work, if I can discipline myself enough, which generally I can't, is trying to get at. What is concurrency for the rest of them? Because, whether it's ChatGPT-3, I'm sure that's really good at doing concurrency, or whether it's just programmers who have got a degree, or maybe they've been to a polytech or a trade school and have learned to program and are now faced with doing concurrency, what do we tell them? And I still maintain, whether it's Swift or whether it's Rust or whether it's OxCaml or whether it's Rock or whatever it is, Forth or even Smalltalk, I don't think we've really got very good answers. Maybe there aren't any good answers, I don't know. But this project was an idea to come up with one take on that, and you'll kind of see where we get to at the end. So now I'm actually going to start on the students' talk. Here we go. This is actually, that's the headline from a different paper for the overall Dala project. The idea effectively was done by Kiko Fernando Reyes, who is not here. He was here, no? He was here, but he's not here anymore. He was That's right. He is now the god of concurrency at Erlang, and he basically tells them not to do anything fancy, I think, and just keeps doing this. And a bunch of other people, most of whom, but not all of whom, were either at Vic or at Uppsala. Concurrent programming is hard, blah, blah, blah. There is a version of this slide that I couldn't find, which at this point, all the little Dala horses start flying around on the screen, so you can imagine that happening, so you can't actually pay any attention to what I'm saying because you're being distracted by all these different things happening simultaneously. Very much like if you're chairing a session at, I don't know, Onward and trying to finish your slides at the same time. While trying to work out why your Daphne program isn't verifying. Anyway, why do I have the next slide? I don't know. Concurrent programming is hard. Why is it hard? Well, we kind of need these things to be correct, and probably most people in the room would agree with that. Simplicity, well, I guess once you start saying for the rest of them, whether it's simple or not and what that means, in fact, is actually a difficult thing to say, but it would be nice. And Dunkley always points about performance. And he says two depressing things about performance. The thing that's depressing, particularly for the functional people, is assignment is always faster than copying. It just is. It's this thing called physics, entropy. Writing to one word in memory is going to be more efficient than copying megabytes, gigabytes. And the other thing which is really depressing for all of us, he says, is, well, why are you writing the concurrent program in the first place? Why are you writing this concurrent program in the first place? I mean, is it just because you like having the CPU meter high? Is it because you like burning your battery life? I mean, you can always get high utilization when you evaluate your programs, but what's actually important is throughput. In other words, your program actually needs to do more work in less time than it would take if you just wrote the sequential program. Because guess what? The sequential program is going to be, it's always going to be a hell of a lot simpler than the concurrent program, and it's more likely to be correct. So if we as programmers are going to waste our time or spend our time or get our LLMs, if you're that way inclined, you're under the age of 20, well, according to the YouTube ads, under the age of 40, and who doesn't know how to use ChatGPT-3, and so I'm not asking it to write my Daphne code for me. It's always going to find writing a sequential program easier than writing a concurrent one, pretty much. We can talk about the elements afterwards. And so if it's not performant, then again, what's the point in doing this? We may as well just let people write their basic programs or whatever it can be done. So what does this come into? So the idea for correctness is what we call the Dala model, which is very much a hypothesis. It's not something I believe. Or maybe it is, I don't know. For simplicity, we had this excuse that we will try with gradual types. We're a long way away from that. Although, once again, we're actually going to touch on that. And for performance, our hope was that we would do this using meta-VM techniques. So things like Graal, at least until, when was it last week that Oracle, whoever it is, Larry Ellison decided to spend the money on yachts instead because he wants to be able to beat New Zealand in a yacht race because we're such a large and important country, whatever. Okay, so what's our take on doing this? Well, we're going to say capabilities for dynamically typed object-oriented language, blah, blah, blah. Okay, support for concurrency. We're not really ready to commit to a single model of concurrency. I think there's either probably another Doug Lee or Alan Perlis quote that says every model of concurrency is wrong. But we kind of feel we have to commit, really, even if we don't really know what it should be, because we have to make progress somehow. We have to come up with some kind of ideas. And what we would like is, along with everybody else in the whole world, to guarantee some sort of data race freedom. That seems kind of important if you want to say, well, what's a good description of what a language is that in some sense is concurrency safe, then you may as well go with data race freedom. Again, for the people who are pushing, disentanglement, which I think means, someone can tell me afterwards if I'm wrong, no data races in the memory allocator, which apparently is a big thing in Haskell, but every other language has had per-thread allocators for probably decades now, so it's not so big in the real world. Anyway, okay, so that's what we're sort of after. For some reason, there's another build. I don't know, there was a little pink horse appearing. Long-term gradual typing, okay, we're a long way away from that. So if you want a second takeaway slide, it's probably this one, which has adorned many of my grant applications, and enough of which got funded for me to still be here, which is why I was only doing the gizzard job slides now rather than 3 years ago. The idea is we're going to coordinate these objects into 3 what we call flavours, because I watch too much physics YouTube when I'm waiting for my Daphne to verify. And those 3 flavours are ISO for isolated, im for immutable, and local for local. Which means pretty much what you think they are if you've done any kind of this. There's another flavour that will appear shortly, but that's the main thing. And the point is here, there is this ownership structure or stratification or whatever you want to call it in this model at this point, which says immutables can only point to other immutables. These things are, values, whatever that means. Shout out to Dimi Rakordon, who isn't in the room, but if she was in the room, she would hear me say, look, there are these values, and she's actually done some interesting work on it, and there was a couple of papers she talked about. Values. Then there are local objects, which, well, they're kind of like thread local objects, not thread local variables like they have in Java, but objects that are going to be confined to a thread. Great, and once they're confined to a thread, you're basically doing sequential programming, but they can refer to other local objects. They can also refer to immutable objects. Have I got this the wrong way? No, I've got this the wrong way, haven't I? And then the third type of these ISOs. And ISOs can refer to immutable objects, but they can't refer to thread local objects. Right, okay, that does make sense. And so the point of ISOs is these are isolated in the sense that Pony or other things are isolated, or if you take the right drugs, you can even see Rust mutual objects as kind of being isolated in the sense that we kind of, well, to quote Tobias's thesis, external uniqueness. You can only have one pointer into this, and that pointer to ISOs can come from an ISO or it can come from a local object. There's an interesting question about whether we should allow immutables to point as ISOs, but that's pointless because, no, we can't allow immutables to point to ISOs. And they don't in my diagram. I was just thinking, could you get away with it? Because there'd be no point because you can't change the pointer to an immutable thing. So the point of ISOs is because you know and have control of the sole incoming reference, you can then hand these off to different threads. And because they can't only point to ISOs, the ISOs will go with them. Because they can point to immutables, the immutables are just out there in the, the Haskell universe. Haskell universe. I guess we've got a Herbrand universe. We've got to have a Didier universe for functional languages. So the Didier universe of all these values, and you can refer to them. But you can't refer to thread local things because you might be moved to a different thread. General side where I make a snide comment about Rust. We can take that as given. So basically these slides just sort of put this all together. Forget what the color coding is. I guess immutables can point to them, and then you can have... Blue is ISO? Oh, blue is... I don't know. You made those slides. I just stole them. Anyway, you can basically... There are these rules about what can point to what. Can we work out? Or on this one, yellow is local, greens are ISO, and blues are immutable. So I was right. I was going to say these things are immutables. And then they can be pointed at by the ISOs, and then in the end, you've got the locals kind of sit at the top of this particular tree. Or tower, I don't know, stratification. There must be some universe, object universes. There we go, right. Some versions of paper then have another one, which I kind of like ignoring because remember that bit I said about concurrency for the rest of them? This is unsafe objects, which I'm really going to try and ignore for the rest of the talk, but it is there if you want to read the paper. It just makes things worse. That was the original version of a slide for various reasons. Again, because I've been watching too much quantum physics and because even I have trouble trying to work out what the difference between a capability, a reference capability, an access permission, an object capability, whatever a capability bit is. I'm trying to discipline myself, not entirely successfully, and I have completely failed to discipline my student into using the word flavour. I'm trying that out to say the objects have flavours. Other things might have capabilities or other things that constrain what flavours they can address or what they can do, but objects have flavours in this system. We all know what a data array is. You still want me to finish half past, yeah? Okay, all right. What does it look like? Well, we'll get there. We will get there. What does it look like? Code kind of looks like this. Because it's based on Grace, which was the language that myself and Andrew Black and Kim Bruce claimed to be producing for educational reasons. And it's not that we've given up, but that COVID came along and then they retired, and I kind of had a different research project to do in order to feed my family. And as I at least said at the time, 15 years ago, God, when we started it, that we said it was an educational language because if we just said, look, we're just kind of do a minimal object-oriented language, everyone would think we were crazy. These days, I would be trying to sell it as, well, it's kind of like a gradually typed version of OCaml. But I'd only describe it that way because OCaml was cool. But if you go back and look at the papers, it does point out that, in fact, there are a lot of things which are very similar to in Grace and to the way that OCaml does. And similarly, it's not accidental that it looks like looks quite a lot like Scala, except we don't say def because we are deaf to the record. Sorry. Have I made a Flavor Flav? No, I haven't made a Flavor Flav joke. Right. On this slide, you can see we're binding ISO. That object there, var account is going to be an object which is ISO, but branch, which is basically just an object with a name, is an immutable, and we can just do kind of stuff with that. The theory is anybody who can read anything from Java or certainly Kotlin on upwards would be able to read Grace without even noticing that they were reading Grace, and more to the point, would then pretty much be able to write it. So, the rest of the paper. So that's that so far. That's the core Dala model, but of course things are never that easy. So the rest of the paper basically looks at 6 different axes of the problem comes when you actually try and build something to do this. So we're going to build a dynamic language to do this, which is what we wanted to do. And the questions are kind of like, well, when are particular things enforced and how are they enforced? It's not just enough to say, well, quoting Hitchhiker's Guide to the Galaxy, it's not just enough to say, well, we want fire, but as Douglas Adams put it, well, do you want fire that can be fitted nasally? If we want an ISO, the question is, well, when are we allowed to use it, and what does it mean that we are actually ISO? So the paper looks at these various alternatives in this axis. So, for example, the staunchest one, which says every time you do with one of these things, you've got to explicitly do a destructive read. In that case, you write this first line and it will crash because var y is reading x, x has got an ISO in it, you're not doing a destructive read. After that, you're left with two variables, same scope, pointing the same thing, bang, you're dead. Another option says, well, maybe you could do it when you do reference something. So we will let you do borrowing, which, if you've been to the talk I gave 3 days ago, doesn't actually exist, but for the purpose of this talk, it does. So you've kind of got this borrowing thing going on. But when you actually try and use an object in any way, at that point, you would kind of kill this thing. You would try and send a message here. And one way to think about it is your VM would just check the reference count on Y, and the reference count on Y isn't 1. So it crashes and said, you are trying to use an ISO that has 2 references. Please find one of them and kill them. And if you think that's worse than the Rust error messages, I couldn't possibly comment. And so, going on, there's basically a bunch of these things. What does it mean to move an ISO? When do you actually do it? If you have an ISO that can move, because that's the whole point of these things. But when you actually consider that the object has actually moved, especially if you are in something that allows borrowing, how do you decide if the thing is no longer borrowed but is actually moved so it can now be accessed from the other thread? And there's a particularly twisted option there, newest, which I don't want to say, to me, feels a bit like what Rust tries to do, which is, we'll let people write the code and we'll get the most permissive interpretation of what their code could possibly mean, which in this case is, you can always use the newest reference, but when it goes away, you can use the next newest reference. And if you think again about Rust borrowing, that's not a bad, well, that is a dynamic analog of what's going on there. Hopefully putting it down this way, you might think why it's horrible. And again, we can look at examples and say, well, this thing will crash under some semantics and won't under others. There's a bunch more of these things I'm finishing up now. Really, I am. About when things are immutable, about where objects get their flavor, and flavor change. Whether an object originally, we didn't think they could change flavors, but some people are keen on this. And so there is a version of this which actually gets you flavor oscillation and superposition and observer dependence in your programming language. Remember what I said about what the aim of this project was at the beginning? For the rest of them? Right. Anyway, I'm going to skip through all that. The paper goes on to say, well, look, what the student has built is, I think, these 5 variants, which he thinks are reasonably coherent combinations of the values on those axes. You can read the paper for more. If you're interested in more, since people are coming in to talk to a talk that has content, there is this definitely one way we can expand this, is where we'd have more flavors. We can have lots more flavors. There are jokes on that slide. I particularly like the last one there. We're scientists. It don't have to be, lose control of our right hand, but the student is actually building this on top of GraceKit, which is our, nth generation low-effort Grace implementation. There was actually a paper about that in MPLR that some people actually liked. And the student is going to go on and do various kinds of evaluation of that. And I put empirical tests in the quote because this is the other thing that people take away from versions of this talk, which isn't actually the point of this talk, but it is the point about why I don't think it's very easy to do empirical student-led or program analysis of these things, which is if you test these kind of different language options with people, what you're testing is the people, not the language design. If you test this with people who learn their concurrent programming in Rust, they will expect it to work like Rust. If you test it with people who learn it in Java, they will expect it to work like Java. Whatever, for whatever languages you've got. Coming to the end, if you remember Yossa Hughes, given that I'm begging for a job, remember how the actor Bernard Hill ended up? He ended up as King Theoden. He was also captain of the Titanic in Titanic, which is pretty damn good for a guy begging for a job. So I'm still maintaining my hope. put perhaps this model somewhere in the back of your head, I probably would now say this is much more simple than what I would like. In some ways, the kind of experiments I'm hoping the student to do, is actually to try and write examples of exemplary or kernel concurrent Dala programs and actually see what idioms are best expressible in what set of conditions. I think that is actually it's qualitative, but it's more useful evaluation than saying we gave it to a group of students, they figured out which version of the language we, as their lecturers who were marking them overall, liked, and told us that one is the best. Sorry, cynicism was showing through. And again, most important thing from this talk is remember this. If the Macintosh was the computer for the rest of us, some of us do need to think about concurrency for the rest of them. Thank you very much.
If you have questions or comments, please come up to the microphone online.
So,
Sorry. There was a handheld mic as well.
Very interesting to me, at least, that there are so very many variations for each of the features that you were considering. Are there any that have not been implemented in languages that you came across because you were investigating? For instance, the one where you allow the alias to the ISO, but you throw an error when you try to call a method on it?
Given the wide swathe of concurrent language design that's been done in the last 30 or 40 years, I think there's probably even weirder stuff out there. I can't necessarily say that I can point at each of the ones we've picked. But it wouldn't surprise me if we had, and it certainly wouldn't surprise me if there are other semantics there that we didn't get. We're not trying to be completely, not trying to be completist in this, at least not at this point.
Okay, so
Thank you.